Now that we have seen so many properties of the Lebesgue measure and Lebesgue measurable sets, it's a good time to look back at what we are trying to do and recall where we started off from. So let me recall our original goals. So we were guided by some geometric intuition which our measures were expected to satisfy. The first one was finite additivity property, and the second one was invariance under translations, rotations and reflections. So we had these two main geometric intuitions in mind when we were trying to define what should be a concept of a measure for arbitrary subsets of Rd. But the Banach-Tarski paradox forced us to look at, separate the classes of subsets of Rd into two classes. Subsets of Rd were divided into two classes, measurable and non-measurable, because the Banach-Tarski paradox establishes the existence via the axiom of choice, the existence of subsets of Rd which fail to have finite additivity. If 2 is assumed, then 1 fails. So we have to divide the subsets of Rd into two classes. The measurable ones were supposed to satisfy 1 and 2, and the non-measurable ones may not satisfy 1 and 2. So we started off with the concept of a Jordan measure, which was defined via the volume of boxes, and then we gradually increased our classes of subsets of Rd in consideration, from boxes to finite union of boxes and then to Jordan measurable sets. But we still felt that even though the Jordan measure respected finite additivity and invariance under translations, rotations and reflections for Jordan measurable sets, but still it was not closed under countable unions and countable intersections, and left out many important subsets of Rd, such as open sets which were not Jordan measurable. So we went further. So the drawback for Jordan measurable measure and Jordan measurable subsets was that it was not a sufficiently large enough class, of subsets. So in particular, open sets may not be Jordan measurable. So since we wanted to have this connection with the topology, underlying topology of the Euclidean space Rd, we wanted to have at least the open subsets of Rd should be measurable in a suitable notion of measure. So this is why we defined the notion of a Lebesgue outer measure and Lebesgue measurability, and we proved various properties such as finite and countable additivity for Lebesgue measurable sets, and we still haven't proved though that Lebesgue measurable sets, the Lebesgue measure for Lebesgue measurable sets is invariant under translations, rotations and reflections. So we have proved this, and of course this is a large class of subsets of RD, large class of subsets of RD that includes all open sets. So this we have also seen, but we haven't seen yet the second property, which is invariance under translations, rotations and reflections. And so this was one of our main geometric intuitions for the properties of the measures that we wanted. So in this lecture we will see this property of invariance of the Lebesgue measure under translations, rotations and reflections. So this is the theorem that we want to prove, which is the Lebesgue measurability under linear transformations of RD. This kind of result we have already seen for the Jordan measure, and this theorem is for the Lebesgue measure. So it says that the first part says that if E is Lebesgue measurable and X is a vector in RD, then the translated set E plus X is also Lebesgue measurable, and the Lebesgue measure of the translated set is the same as the Lebesgue measure of the original set. And the second part says that if E is Lebesgue measurable and L is a linear transformation of RD, then the image of E under L is a Lebesgue measurable set, and the measure transforms as we would expect, which is it is a multiple of the measure of E, and the multiple is given by the modulus of the determinant of L. So in this way, this is an extension of the transformation for Jordan measurable sets, and this shows also that from the second part that this is M of LE is equal to M of E if L is a translation, is a rotation. Translation we have already seen is a rotation or a reflection, because if L is a rotation or a reflection, then it is an orthogonal matrix, and an orthogonal matrix has determinant 1. So we have MLE equals ME. Of course, the first part is translation invariance, and the second part is rotation invariance and reflection invariance. So in this way we have we would have proved the geometric intuition that we started off with, which is the measure should satisfy this invariance under translations, rotations and reflections, and it should satisfy finite subadditivity also. Since we have already seen countable additivity, we only have to prove this invariance under translations, rotations and reflections. So let's see how this is proved. So to prove this, so let's write first what we want, what we are going to use to prove this. To prove both 1 and 2, we will use the following lemma, which gives another equivalent characterization for Lebesgue measurability, which is that E is a Lebesgue measurable subset of RD if and only if for any epsilon greater than 0 there exists a closed subset, closed set F, and an open set U which contains E, such that the measure of U minus F is less than or equal to epsilon. So one can just use the inner approximation by closed sets and outer approximation by open sets to prove this equivalence, that E is Lebesgue measurable if and only if this condition holds. So let's see how we use this lemma to prove the first part. So first we will show that, if E is Lebesgue measurable, then E plus X is also Lebesgue measurable. So using the lemma for any epsilon greater than 0, we choose U which contains E and is open, and F which is a subset of E and is closed, such that the measure of U minus F is less than or equal to epsilon. Now note that U open is equivalent to saying that U plus X is open, and U closed, or rather F closed is equivalent to saying that F plus X is closed. This is because the reason is that the translation map tau x from RD to RD, which takes y to y plus x, is a continuous bijection. So it is a homeomorphism of RD. So this means that it takes open sets to open sets and closed sets to closed sets, and so we have that if U is open, it is equivalent to saying that U plus X is open, and if F is closed, then F plus X is closed, and vice versa. Note also that F plus X is a subset of E plus X is a subset of U plus X, and this is an open set and this is a closed set. So it suffices to show that the measure of U plus X minus F plus X is less than or equal to epsilon. So for this I claim two things. First is that the measure of U plus X, U plus X minus F plus X is equal to U minus F plus X, which implies that the measure of U plus X minus F plus X is equal to the measure of U minus F plus X. And the second is that if V is an arbitrary subset, is an arbitrary open subset, then M of V plus X is equal to M of V. So with these two things we can immediately conclude. So assuming that these claims, assuming the claims above, we have that the measure of U plus X minus F plus X is equal to the measure of U minus F plus X. And now note that this is an open set because U is open and the complement of F, which is closed, is open. So it's an intersection of two open sets, therefore it is open. So by 2, so this is by for first part. The second part then shows that this is simply M of U minus F, and this is less than or equal to epsilon. So we are done. So we just have to show the claims. So the first part is very easy. It's just a set theoretic argument, so I leave it as an exercise. So I will prove only the second part. So proof of 2. So since V is open, it is an, we can write V as a countable union of boxes Bi, collection. So Bi n equal to I equal to 1 to infinity, a collection of almost disjoint closed boxes in Rd. So we have shown this, we have used this lemma before. I didn't prove it, but I referred to Terence Tao's book for a proof that any open set is a countable union of almost disjoint closed boxes, in fact cubes, in Rd. So this implies that M of V is the sum of MBI I equal to 1 to infinity. Now note that if V can be written as the union of BI's, then V is equal to is the union of these BI's. This implies that V plus X is then the union of the sets Bi plus X I equal to 1 to infinity, and note that Bi plus X I equal to 1 to infinity is also a collection of almost disjoint closed boxes in Rd. And we already know that the translation invariance holds for boxes. So we have the measure of the M of V plus X is equal to the sum Bi plus X I equal to 1 to infinity. This is nothing but I equal to 1 to infinity M Bi, because Bi's are elementary, and we have shown that translation invariance holds for elementary sets, even Jordan measurable sets. So we get MV on the right hand side. So MV plus X is equal to MV for any open set V. So this proves that our second claim, and since I have already left the first as an exercise, then it shows that E plus X is Lebesgue measurable. Now we still have to show that E plus X, to show that the measure of E plus X is equal to the measure of E. So first suppose, to show this, first suppose that the measure of E is finite. Okay. Then there exists an open set U containing E such that measure of U is less than or equal to measure of E plus epsilon. So I am going to fix epsilon greater than 0 and then if measure of E is finite, then you can find an open set containing E such that the measure of U is bounded above by measure of E plus epsilon. Now E plus X is contained in U plus X, and this is an open set. So the measure of E plus X, so I am writing measure because we have already shown that I am writing M instead of M star because I have already shown that E plus X is Lebesgue measurable. So this is less than or equal to Mu plus X by monotonicity, and this is equal to Mu by the translation invariance for open subsets that we have proved, and this is less than or equal to me plus epsilon for any arbitrary epsilon. This implies that me plus x is less than or equal to me, since epsilon was arbitrary. Now this holds for any Lebesgue measurable set E and any vector x. So I am going to put E prime as E plus x and x prime as minus x. So this implies that measure of E prime plus x prime is less than or equal to measure of E prime by what we have just shown, but E prime plus x prime is nothing but E, because it is E plus x minus x. So the left hand side is just E and the right hand side is E plus x. So we have shown that me plus x is less than or equal to me. So this is the first inequality, and the second inequality is the reverse one. So this concludes the proof that me equals, so let me write it here, me equals me plus x. Now let's come to the second part, part 2, which is a more interesting, if you want, that if L is a linear transformation, then E being Lebesgue measurable implies that LE is Lebesgue measurable, belongs to LRD, and the measure of LE is precisely modulus of the determinant times me, where the equality holds in the extended real numbers, so both sides can be plus infinity as well. Nevertheless, this equality holds. So let's see the proof for this statement. So we have to start with the case when the rank of L is strictly less than the dimension D on which it is defined. So we expect that the image will lie in a hyperplane of dimension strictly less than D, and so it should have measure 0, just as in the case of the Jordan measure. But for this to be proven, we need the following lemma to show that a hyperplane, any hyperplane H belongs to the class of Lebesgue measurable sets and the measure is 0. So we already know that bounded segments of hyperplanes are Jordan measurable, and they have Jordan measure 0. So if we can write the hyperplane as a countable union of disjoint bounded segments of hyperplanes, then the resulting thing will be Lebesgue measurable and the measure will still be 0 because each component will have measure 0. But we still need to prove that if a bounded segment is Jordan measurable, then it is Lebesgue measurable, because the two things have different definitions. So we still haven't shown this lemma, that this is another lemma. It's interesting in its own right, that any Jordan measurable subset, Jordan measurable set E is Lebesgue measurable. So let me write, this is lemma 1 and this is lemma 2. So first let's see how lemma 2 implies lemma 1. So this is because any bounded segment meaning a subset of the hyperplane which is bounded. So I am calling this a bounded segment of a hyperplane. H is Jordan measurable. So this we have proved before. So this implies that let me denote the bounded segment as C. This implies that C is Lebesgue measurable, and then we can write H as the union of H intersection the closed wall of with center 0 and radius n equal to 1 to infinity. So this is now a countable, each one is Lebesgue measurable because it is Jordan measurable, Lebesgue measurable, and so this implies that H is Lebesgue measurable. And so the measure of H is bounded above by the measure of these bounded segments n equal to 1 to infinity, and because it is Jordan measurable, we have seen that the outer Lebesgue outer measure coincides with the Jordan measure for Lebesgue measurable sets. So it implies that this is 0 for each n, and so this is 0, and therefore the measure of H itself is 0. So lemma 2 implies lemma 1. So let's try to show that any Jordan measurable set is Lebesgue measurable, and I should add here and the Lebesgue measure ME is equal to the, so let me write Lebesgue, because we are using both for both notations we are using M. So on the left hand side we have the Lebesgue measure, which is by definition the restriction of the Lebesgue outer measure to Lebesgue measurable sets, and on the right hand side we have the Jordan measure. So we have shown that the Lebesgue outer measure coincides with the Jordan measure for Jordan measurable sets. So any Jordan measurable set is Lebesgue measurable, and of course the measures do coincide. So let's see how to prove lemma 2. So proof of lemma 2, this is quite easy. Remember that E is Jordan measurable, has the following equivalent characterization: for epsilon greater than 0 there exists elementary sets A and B such that A is a subset of E is a subset of B, and the measure, the elementary measure of B minus A is less than or equal to epsilon. So now we are going to show that E is Lebesgue measurable. To show E is Lebesgue measurable, so we will again use the characterization that we have just used, which is that for any epsilon greater than 0 there exists a closed subset F of E and an open subset U of E such that the measure of U minus F is less than or equal to epsilon. So I am going to produce U and F by modifying A and B. So modify A to get a closed elementary set F such that the measure of F is greater than or equal to the measure of A minus epsilon. So when we were trying to show countable additivity, we have used this fact that we can have control over the volume of the elementary sets, so that we can get closed and open sets respectively. So here we have taken a closed elementary subset f of A such that this is true, and then modify B to get an open subset, open elementary subset U containing B such that the measure of U is less than or equal to measure of B plus epsilon. So note that all these measures are that we have here are finite, because E is Jordan measurable, so by definition it is bounded, and so all these measures are in fact finite. And so here we can immediately get that m of u minus f is equal to mu minus mf, because this is finite things, and this is less than or equal to mb plus epsilon minus ma minus epsilon, which is equal to m of b minus a plus 2 epsilon, and this is less than or equal to 3 epsilon. So in fact we have shown that this is less than or equal to 3 epsilon in the criteria for Lebesgue measurability, which is still fine because it's still an arbitrary number, 3 epsilon. So E is Lebesgue measurable. So now going back to the linear transformation L, if L has rank less than, strictly less than D, then the image of L is a subset of some hyperplane, is a subset of some hyperplane H, which implies that LE, the outer measure of LE is less than or equal to the outer measure, which is the Lebesgue measure of the hyperplane H, and this is 0 as we have shown. So this implies that the outer measure of LE is in fact 0, which implies that LE is Lebesgue measurable, as well as the fact that m of LE is equal to modulus of the determinant of L times ME, because this is precisely 0. So for the case when the rank is strictly less than D, this is fine.